Partial fraction expansions. Let's begin here with an example. Suppose we wish to find the indefinite integral of 6 divided by x cubed minus 5x squared plus 6x. We notice that the denominator can be factored into x times x minus 2 times x minus 3. And it turns out we can take advantage of this as follows. We imagine that this integrand is the result of adding 3 terms, each of which has one of the factors as its denominator. In other words, we surmise that the integrand is equal to a constant a divided by x, plus a constant b divided by x minus 2, plus a constant c divided by x minus 3. And if we can determine a, b, and c, the integration will be easy. This is called a partial fraction expansion or partial fraction decomposition. So let's find a, b, and c by first multiplying each side by the denominator on the left. That leaves 6 on the left, and the first term on the right becomes x minus 2 times x minus 3 times a after cancellation of x. The second term becomes x times x minus 3 times b after cancellation of x minus 2. And the third term becomes x times x minus 2 times c after cancellation of x minus 3. At this point, there are multiple ways to proceed. One particularly simple approach is to plug in 3 carefully chosen values of x. Notice that if we plug in x equals 0, then the equation becomes 6 equals 6 times a plus 0 times b plus 0 times c. So right away we find that a must equal 1. Now let's notice that if we plug in x equals 2, then the coefficient of a becomes 0 and the coefficient of c becomes 0. The coefficient of b is minus 2, so we have 6 equals minus 2b, which tells us that b is equal to minus 3. Now let's plug in x equals 3. That makes the first 2 terms on the right equal 0, and it makes the coefficient of c on the right equal 3. So 6 equals 3c, which tells us that c is equal to 2. So our partial fraction expansion is 1 over x minus 3 over x minus 2 plus 2 over x minus 3. Now each term here has the form of a constant times du over u, so each results in a multiple of a natural log term. The first term gives us the natural log of absolute value of x. The second term gives us minus 3 times the natural log of the absolute value of x minus 2. And the third term gives us plus 2 times the log of the absolute value of x minus 3. And then we add our c, and we've got the indefinite integral. Finally, let's note that it's possible to use log properties to combine all 3 log terms into one. We are concerned here with integrating rational functions f of x equals n of x divided by p of x, where of course the numerator and denominator are polynomials, and the degree of the numerator is less than the degree of the denominator. That is, f is a proper rational function. Note that if the degree of the numerator is greater than or equal to the degree of the denominator, then by division f of x can be expressed as a polynomial plus a proper rational term. For example, the rational function x squared over x squared minus 2x minus 3 is not proper, and we can use long division to express it as a polynomial plus a proper rational term. Dividing x squared minus 2x minus 3 into x squared, we note that x squared goes into x squared 1 time, so now we multiply 1 times our divisor there, and then subtract, and we get a remainder of 2x plus 3. So that rational function is equal to the quotient 1 plus the remainder 2x plus 3 over the divisor x squared minus 2x minus 3. So here we have a 0-degree polynomial, the constant term 1, plus a proper rational function. Another example, x cubed over x squared minus 2x plus 1. Here the degree of the numerator is 1 more than the degree of the denominator. Let's do long division here. X squared goes into x cubed x times. Then we multiply x by the divisor, and then subtract, and we get 2 times x squared minus x. Now we take another step. X squared goes into 2x squared 2 times. We multiply by 2 and subtract, And now we have a remainder of 3x minus 2. So this rational function is equal to the quotient x plus 2 plus the remainder 3x minus 2 over the divisor x squared minus 2x plus 1. So again, that's a polynomial plus a proper rational term. The fact that this is always possible is why we're concentrating solely on proper rational functions. Let's assume that the denominator p of x factors as a constant a times a product of linear factors raised to powers times a product of quadratic factors raised to powers, where the quadratic factors are irreducible. That is, they have complex zeros and so can't be factored any further with real coefficients. Algebraic theory tells us that this is always possible and that the factorization is unique. Then f of x may be expanded into a sum of terms whose forms may be predicted as follows. Each nth power of a linear factor x minus r contributes n terms to the sum. Each power of x minus r, from the first power to the nth power, appears in one of the denominators, and every numerator is a constant. And each nth power of an irreducible quadratic factor contributes n terms, where each power of the quadratic factor, from the first power to the nth power, appears in one of the terms, and every numerator is a general linear expression, a constant times x plus a constant. For example, in the function 1 divided by x cubed times x squared plus 1, we have a linear factor x raised to the third power and an irreducible quadratic factor x squared plus 1 raised to the first power. The x cubed in the denominator contributes a over x cubed plus b over x squared plus c over x, and the quadratic factor gives us a term of the form e times x plus f over x squared plus 1. And we're guaranteed that constants a through f exist to make this true. Another example. X squared divided by x minus 1 times x squared plus 1 quantity squared. Here, the x minus 1 factor in the denominator is a non-repeated linear factor. It will contribute only one term, a divided by x minus 1. The quadratic factor x squared plus 1 is to the second power, so it contributes two terms, bx plus c divided by x squared plus 1 squared plus dx plus e divided by x squared plus 1 to the first power. Here's another example. X cubed divided by the square of x squared plus 2x plus 2. The quadratic formula will convince you that x squared plus 2x plus 2 has no real zeros and so can't be factored without using complex numbers. And let's also note that this is in fact a proper rational function. The degree of the numerator is 3, the degree of the denominator is 4. So we simply have a repeated quadratic factor in the denominator, so we'll have two terms, a linear expression divided by the quadratic factor squared, plus another linear expression over the quadratic factor to the first power. Let's emphasize here that it's extremely important to get a good understanding of how this is done, because if the proper general expansion is not written down correctly, one can proceed to find coefficients without running into any difficulty, but the end result is something that is not equal to the original function. So be careful. Now let's look at another example. Let's find the indefinite integral of 1 over x cubed minus 2x squared dx. Let's factor the denominator there into x squared times x minus 2. Now we need to do a partial fraction decomposition on 1 over x squared times x minus 2. Because of the x squared in the denominator, we need to write a divided by x squared plus b divided by x, and then the x minus 2 factor tells us to write c divided by x minus 2. Now let's multiply through by x squared times x minus 2, and we have 1 on the left side, and the first term on the right is x minus 2 times a, then the second term is x times x minus 2 times b, and the third term is just x squared times c. This time, let's multiply out the right-hand side. Notice that the only constant term we'll have is minus 2a. Also notice that the coefficient of x will turn out to be a minus 2b. So we have a minus 2b times x, and the coefficient of x squared will be b plus c. Now we're going to find a, b, and c by equating coefficients. The left side of the equation is just 1, Let's think of that as 1 plus 0 times x plus 0 times x squared. Now, in order for this equation to be true for all x, the coefficients have to be the same on both sides. The constant terms have to be the same. That tells us that 1 equals minus 2a. The coefficients of x have to be the same, so 0 has to equal a plus 2b, and the coefficients of x squared have to be the same, so 0 equals b plus c. Now, if we start with the first of these equations, we get a equal to minus 1/2, and knowing that a equals minus 1/2, the second equation becomes 0 equals minus 1/2 minus 2b, which tells us that b is minus 1/4, and knowing that b is minus 1/4, the third equation tells us that c equals plus 1/4. So our partial fraction expansion is minus 1/2 divided by x squared plus minus 1/4 divided by x plus 1/4 divided by x minus 2. Now we integrate the first term there using the power rule. It's minus 1/2 times x to the minus 2, so we end up getting plus 1/2 times x to the minus 1. The second term gives us minus 1/4 times the natural log of absolute value of x, and the third term gives us plus 1/4 times the natural log of the absolute value of x minus 2. And we add our constant c, and we've got our indefinite integral. Now notice that the two log terms can be combined. By factoring 1/4 from those two terms, the other factor is the natural log of absolute value of x minus 2 minus the natural log of absolute value of x, and so we can write this as 1/2 of 1 over x, or 1 over 2x, plus 1/4 the natural log of the absolute value of x minus 2 divided by x, plus c. Here's another example. Let's find the indefinite integral of x squared divided by x squared minus 9 quantity squared. Now notice that the quadratic x squared minus 9 is not irreducible. It factors into x plus 3 times x minus 3. So the complete factorization of the denominator is x minus 3 squared times x plus 3 squared. So we now need to do a partial fraction expansion on x squared divided by x minus 3 squared times x plus 3 squared. That denominator consists of two repeated linear factors. The x minus 3 squared tells us to write a divided by x minus 3 squared plus b divided by x minus 3, and x plus 3 squared tells us to write c divided by x plus 3 squared plus d divided by x plus 3. So, as usual, let's start by multiplying through by the denominator on the left to clear the fractions. That gives us x squared on the left. The first term on the right is x plus 3 squared times a. The second term becomes x plus 3 squared times x minus 3 to the first power times b. The third term is x minus 3 squared times c. And the fourth term is x minus 3 squared times x plus 3 times d. Now we're going to go as far as we can, plugging in good choices of x. Notice that if we plug in x equals minus 3, then the left side is 9, and the coefficients of a, b, and d are all 0. The coefficient of c is negative 6 squared, or 36. So right away we know that c is equal to 9 divided by 36, or 1/4. Now let's plug in x equals 3. Again, the left side is 9, and this time the coefficients of b, c, and d are all 0. The coefficient of a is 6 squared, or 36, and so we easily get that a is 9 divided by 36, or 1/4. Now we've essentially exhausted this approach. There are no other values of x that will let us determine b and d in the same way. So let's take the values of a and c that we've found and put those into our equation and rewrite the known terms on the left, x squared minus the a term minus the c term. That will equal the b term plus the d term. Now let's simplify what's on the left. First let's factor out a 1/4. Now when we multiply out x plus 3 squared and x minus 3 squared, we will see a 4x squared minus x squared minus x squared for a 2x squared. Each of x plus and minus 3 squared gives a 9, so we'll have a minus 9 for a minus 18. And the middle terms that we get from squaring x plus and minus 3 have opposite signs, so they will add up to 0. So what's in the parentheses there becomes simply 2x squared minus 18. Now if we factor 2 there, that becomes 1/2 of x squared minus 9, and x squared minus 9 factors into x plus 3 times x minus 3. So now let's divide through by x plus 3 times x minus 3, and we have 1/2 equal to x plus 3 times b plus x minus 3 times d, and now we can determine b and d by plugging in x equals minus 3 and plus 3. Plugging in minus 3 gives us 1/2 equals 0 times b minus 6d, which tells us that d is minus 1/12, and x equals 3 gives us 1/2 equals 6b minus 0d, which tells us that b is positive 1/12. Now, noticing that we can factor out 1/12, we'll write our problem as 1/12 of the integral of 3 divided by x minus 3 squared plus 1 divided by x minus 3 plus 3 divided by x plus 3 squared minus 1 divided by x plus 3. So now we're ready to integrate. If we substitute u equals x minus 3 in the first term, then dx and du are the same thing, so that term looks like 3 du over u squared, which would give us a minus 3 u to the minus 1, so that term ends up giving us a minus 3 over x minus 3. Now the second term is x minus 3 to the minus 1 power, so that gives us a natural log of the absolute value of x minus 3. The third term is similar to the first. That gives us minus 3 over x plus 3 to the first power, and the last term is similar to the second one. We'll get a minus natural log of absolute value of x plus 3 there, and then we add our plus c. And now notice that we can combine the log terms, and we can also combine the two fractions there, and write this as 1/12 of the natural log of the absolute value of x minus 3 divided by x plus 3, minus 3 over x minus 3 minus 3 over x plus 3, which ends up being minus 6x over x squared minus 9. Another example. Let's look at the integral of x squared over x plus 1 times x squared plus 4. This denominator is already completely factored. X squared plus 4 is an irreducible quadratic. So we need to do a partial fraction expansion on x squared divided by x plus 1 times x squared plus 4. Since we have two non-repeated factors there, we'll just have two terms. The first one is a divided by x plus 1, and the second one is bx plus c divided by x squared plus 4. Now, as usual, let's multiply through by the denominator, and we have x squared equals x squared plus 4 times a plus x plus 1 times bx plus c. Now let's notice that if we plug in x equals minus 1, the second term on the right will be 0, and the equation becomes 1 equals 5a plus 0. So we immediately have that a is equal to 1/5. Now let's put that value of a into our equation, and then expand and simplify the right-hand side. Notice that the coefficient of x squared on the right-hand side will be 1/5 plus b, and the coefficient of x on the right-hand side will be b plus c. And the constant term on the right-hand side is 4/5 plus c. Now we'll equate coefficients. The coefficient of x squared needs to be 1, so that tells us that b is 4/5. The coefficient of x must be 0, so c equals minus b, or minus 4/5. The constant term ends up being 0 automatically. So a is 1/5, b is 4/5, c is minus 4/5. And by factoring out a 1/5, we can write our integral as 1/5 times the integral of 1 over x plus 1 plus 4x minus 4 divided by x squared plus 4. Now, in order to deal with that second term, we need to break it up into 2 and write it as 4x divided by x squared plus 4 minus 4 over x squared plus 4. Now, the first term is simply going to give us a natural log of the absolute value of x plus 1. In the second term, notice that the derivative of the denominator is 2x, so the numerator is 2 times the derivative of the denominator, so that means we're going to have 2 times the natural log of the denominator. A simple way to handle the third term is to divide the numerator and denominator by 4 and rewrite that term as minus 1 over x divided by 2 squared plus 1. We'll then think of making the substitution u equals x over 2, or x equals 2u, which means that dx is 2 du, and with that substitution, the term becomes minus 2 du over u squared plus 1. that will give us a minus 2 times the inverse tangent of u, and u is x divided by 2. So that's minus 2 times the inverse tangent of x divided by 2. And adding plus c completes the problem. Now let's look at an example that involves a repeated irreducible quadratic factor. Let's find the integral of x cubed divided by the square of x squared plus 2x plus 2 dx. It will make our work a good bit easier here if we complete the square and rewrite that quadratic as x plus 1 quantity squared plus 1. We can then make a substitution of u equals x plus 1 and du equals dx to rewrite the integrand as the cube of u minus 1 divided by the square of u squared plus 1. Now there's a little bit of a trade-off there. The numerator has become more complicated, but the denominator has become very nice. So now let's perform the partial fraction expansion for u minus 1 cubed divided by u squared plus 1 squared. Now we're going to need to multiply out the numerator. Turns out that u minus 1 cubed is equal to u cubed minus 3u squared plus 3u minus 1. Now the partial fraction expansion will have the form of au plus b over u squared plus 1 squared plus cu plus d over u squared plus 1 to the first power. Now let's multiply through by the denominator, and we have the expanded numerator u cubed minus 3u squared plus 3u minus 1 equal to au plus b plus u squared plus 1 to the first power times cu plus d. Now let's multiply out the right-hand side. In doing that, we multiply u squared times c times u, which gives us a c times u cubed term. The only u squared term comes from d times u squared. Now we have au and we have cu times 1, so the coefficient of u is a plus c. And we have b plus d times 1, so the constant term is b plus d. Now we'll equate our coefficients. We want the coefficient of u cubed to be 1 on both sides, so that tells us that c is 1. The coefficient of u squared on both sides is minus 3, so d is minus 3. The coefficients of u need to be the same. That tells us that a plus c must equal 3, but we already know that c is 1, so a must be 2. And the constant terms must be the same, so b plus d equals negative 1, but we already know that d is minus 3, so b must be positive 2. So we have our expansion. 2u plus 2 divided by the square of u squared plus 1 plus u minus 3 divided by u squared plus 1. Now to integrate those two terms, we'll need to break each one of them into two parts. So let's first write the integral of 2u over u squared plus 1 squared plus 2 over u squared plus 1 squared, and then plus u over u squared plus 1 minus 3 over u squared plus 1. So now we're ready to antidifferentiate. Notice that in the first term, the numerator 2u is exactly the derivative of what's inside the square in the denominator. So if we were to substitute, say, v equals u squared plus 1, this would become dv over v squared, which would give us a minus 1 over v, so that term contributes a minus 1 over u squared plus 1. The second term is more complicated. Let's leave that alone for now. That's going to end up requiring a trigonometric substitution. Notice in the third term that the numerator is just 1/2 of the derivative of the denominator, so we're going to get 1/2 of the natural log of the denominator. And the last term is just minus 3 times the derivative of the inverse tangent of u. So now we've got everything except the integral of the second term. So let's compute that. This calls for a tangent substitution. We'll let u equal tangent theta, which makes du equal secant squared theta d theta. Now the denominator in the integrand is going to be the square of tangent squared plus 1. That's the square of secant squared, so that's secant to the fourth, and our numerator is going to be 2 secant squared theta d theta. So this simplifies to give us 2 divided by secant squared, and 2 divided by secant squared is just 2 times cosine squared. Now let's recall that cosine squared is 1/2 of 1 plus cosine 2 theta. So 2 times cosine squared is 1 plus cosine of 2 theta, and integrating that gives us theta plus 1/2 of sine 2 theta, and 1/2 of sine 2 theta is sine theta cosine theta. The theta here is simply going to be the inverse tangent of u, and we'll get sine theta and cosine theta from this triangle with opposite side u, adjacent side 1, and hypotenuse the square root of u squared plus 1. So the sine of theta is u over the square root of u squared plus 1, and cosine theta is 1 over the square root of u squared plus 1. We multiply those factors together, and we get u over u squared plus 1. So our indefinite integral is inverse tangent of u plus u over u squared plus 1 plus c. So now let's go back to our original u integral, the integral of the cube of u minus 1 over the square of u squared plus 1. We have the first and third terms there, minus 1 over u squared plus 1 1/2 of the natural log of u squared plus 1. The second term contributes a u over u squared plus 1, as well as the inverse tangent of u. We'll combine that inverse tangent of u with minus 3 times inverse tangent of u to write minus 2 times inverse tangent of u, and we add our plus c. Now let's simplify this a bit by combining the first two terms here. We have a common denominator of u squared plus 1, so this is u minus 1 over u squared plus 1. And so now all we need to do is replace u with x plus 1. So our original integral becomes x divided by the square of x plus 1 plus 1 plus 1/2 the natural log of the square of x plus 1 plus 1 minus 2 times the inverse tangent of x plus 1 plus c. Now finally let's remember that x plus 1 squared plus 1 is just the quadratic factor x squared plus 2x plus 2 in the denominator of our integrand, so it's not a bad idea to express our final answer using that expanded form.